Hello. In a previous video on a derivation of the SUVAT equations of motion, I mentioned that when it comes to the third and fourth equations, which we see here, the third equation and the fourth equation, that there's another way to think about them. And so I thought in this video that I would just spend some time highlighting and talking about that point. So I'm just going to get rid of this, which happens to be a derivation of the fifth equation, and really we want to focus on the third and fourth equations. Now, I suppose what's interesting, perhaps it's useful, I don't know, but we can think about the third and fourth equations similar to how we did the first and second equations, and that is directly in relation to velocity time graph. So I'm going to draw one velocity time graph here. Okay, and we can again, I'm just going to I'll just label this velocity, and just going to pick an arbitrary point, as I did in the previous video. Call it, it's our initial velocity u, t equals 0, and but instead I'm going to just box this off, and I'm going to create a triangle like so, and we've got a rectangle here at the bottom. And we'll call this area A, and this is area B. And we can say that from this point here to this point here is T. And I'm just setting up this graph, and at this point here we can write this as going up. We can say that this is if this is V U, we can say that this is V minus U, this part right here. I go like this, something like this, and this whole thing, of course, is velocity V at the time, right? And so I suppose what's interesting about this is that to derive the third and fourth equations, we talked about how we'll start with the third equation. We're substituting equation 1 into equation 2. And another way to think about that is by looking at this velocity time graph. And really, I suppose if area A, and I'll just call it A, subscripts A, area A equals ut, right? Our initial velocity times our time is going to get us area A, ut, and area B, which I'll just say area subscripts B, equals 1/2 V minus U times T. Is that right? 1/2 times V minus U times T. Yeah. Okay. So that's our area that's how we find our area for B and area for A, right? So really, another way to think about it is that if we add the areas of the triangle and the rectangle, what do we end up with? Well, let's write that over here, or actually I'll write it down here. If we add these two areas, what do we end up with? Well, we end up with and maybe I'll denote it this way: area subscript A plus area subscript B equals ut plus 1/2 V minus ut. Right, we're adding these two areas. I don't know, I can maybe mark that in a color or something, like, see, we're adding these two areas, right? And that leaves us with ut plus 1/2 times V minus ut. Now, I suppose the curious step here is that Vu from equation 1 we can say equals AT. So if we have equation 1, we have V equals UAT, so V equals U plus AT. Well, we can rewrite this, can't we? Where AT equals V minus U. Well, here's V minus U, so we can just substitute AT here. And I'm just going to erase this for the sake of space. And by doing so, we can sort of simplify. We can simplify all of this where we have UT plus 1/2 AT squared. AT squared. And that just so happens to be the third equation of motion as we have right here. And actually I should write, because it's the total area, as I said, we're adding these two, the triangle and the rectangle, so that's going to be our total displacement. And so S equals UT plus 1/2 AT squared. Now, similarly, we can think about the fourth equation in the same way, or in a very similar way, I should say. And I'm not quite sure how to. Actually, what I'll do is I'm just going to cut this, and I'll paste it down a little bit lower, if it will let me, yes, and just to create space, because we're going to use a slightly different graph. So this is the fourth equation. This is from the derivation in the first video. Now, what we want to do is set up a velocity time graph again, so we can think about this equation in relation to the graph. And I'll just draw it right here. And so again, we've got velocity right here, and we've and I suppose what we want to do again is kind of an arbitrary point U, its initial velocity, right? We're going to draw our line up just as we did in the first video, but instead now I'm going to again box this off as I did before, and instead we're also going to consider this triangle here. I don't know, maybe I'll denote it with a dotted line like this, right? So this entire rectangle is what we're going to consider, the area of this entire rectangle, like this. Or maybe actually, yeah, I'll just, oh no, okay, I'll just leave it like that. I was going to denote both in separate colors, but I don't think that's necessary. Okay, so let's just call this area C, right? Area C, similar to the previous example, and we'll call this area D, right? And I suppose, well, actually, I'll do it this way. So this is area C, this triangle, but this entire rectangle here, and I'll denote this in a separate color to make it very clear. This entire rectangle, like this, that's area D. Area D. So area D is this entire thing, and area C is just this triangle. And we can denote this, of course. This is velocity, total velocity here, velocity, final velocity, and of course this is time, right? And this is the time from 0 up to that point of reaching final velocity, so t. And so yeah, basically now if area C, which I'll write here, area C, I'll just actually write it this way, area subscript C equals, it's a triangle, so it's going to be 1/2, and of course it's v, final velocity v, right? So it's going to be 1/2 times v minus u times the time taken, right? So t is, and that's just the area for this triangle. And then we've got area D, area subset D, which is this whole rectangle. So what's that? Well, that's just going to be for this entire rectangle here. That's just going to be length times width, right? We think of that, length times width. If I just mark it all, right? So this entire area D is just going to be length times width. Well, what is that? That's v times t. So it's going to be vt. Area D is vt. And now, to find the area under the line, which is essentially the entire point here, we want to subtract the area of the triangle, area C, from the large rectangle, right? From area D, which gives us similar algebra to the previous example in considering the third equation. And so we want to subtract, as I said, we want to subtract this from area D. And so to do that, if I write this here, we can say that it's AD d minus ac, and what we end up with is vt minus 1/2 v minus u times t. Now, just like just as in the previous example, where we found that if we rewrite the initial equation v equals u plus at, if we rewrite that so at equals v minus u, right, then we can just say that this is at. And what ends up happening here, and again, this point is pretty straightforward. We just say that a subscript d minus area c equals vt minus 1/2 at squared. Right, and that's exactly what we found in our initial derivation. And actually, I should put this is the total area here, area d, right? This total area right here, right? So total displacement s equals vt minus 1/2 at squared, just as we found in our original derivation.